On which side of the screen do you think is work being done? Work is being done only on the left side of the screen, where we see that a block is being pushed across the floor. Even though in the second case, the wooden crate is being pushed, there is no work being done. This is because, in physics, work is said to be done only when an applied force succeeds in moving a body. Consider a wooden block which is at rest on a horizontal surface. When the block is pulled by an external horizontal force F, it is put into motion and is displaced through a certain distance d, and we say work is done on the block. Let's consider a second case, where the direction of the force is not along the direction of the motion of the block. Here, the force makes an acute angle theta with the horizontal. In this case, too, we observe that the block moves in the horizontal direction only. Here, the total amount of force is not being utilized to move the block. Only the component of the applied force along the direction of the displacement is responsible for the motion of the block. This component is F cos theta. Thus, here, the work done on the block by the force is the product of F cos theta and displacement. In this expression for the work done, both F and D are vectors, whereas the product, work done, is a scalar. Thus, this quantity Fd cos theta is called the scalar product of the two vectors F and D. In vector form, it is denoted by a dot in between the two as shown, and is read as F dot D. Hence, it is also referred to as the dot product. Now let's understand dot product in detail. The dot product of two vectors A and B is equal to the product of the magnitude of the two vectors and cosine of the angle between the two vectors. The result of a dot product is always a scalar. Now, let's see some properties of the dot product of vectors. 1. The dot product of vectors is always a scalar quantity. 2. The dot product is commutative. Consider the two vectors A and B inclined as shown. Theta is the angle between the two vectors. The component of one vector in the direction of the other is called the projection of the vector on the other vector, and is denoted by the product of the magnitude of the vector and the cosine of the angle between them. Hence, we see that B cos theta is the projection of vector B on vector A. So, the dot product of vectors A and B can be written as A into B cos theta, which is equal to AB cos theta. Let this be equation 1. Similarly, we see that A cos theta is the projection of vector A on vector B. So, the dot product of vectors A and B can be written as B into A cos theta, which is equal to AB cos theta. Let this be equation 2. From equations 1 and 2, we see that A dot B is equal to B dot A, which is equal to AB cos theta. Thus, the dot product of two vectors is commutative. The dot product obeys the distributive law. So, A dot B plus C is equal to A dot B plus A dot C. All dot products obey the rule M times A dot N times B is equal to Mn times A dot B, where M and N are just constants. Consider the unit vectors along the Cartesian coordinate axis I, J, and K. The angle between any two vectors in the same direction is 0. Thus, when the two vectors are parallel and in the same direction, then the magnitude of their dot products is maximum, as cos 0 degrees is equal to 1. Thus, we get I dot I equals 1, as shown. Similarly, we get J dot J and K dot K equal to 1 as shown. The angle between any two mutually perpendicular directions, that is, between I and J, or J and K, or K and I, is 90 degrees. And cos 90 degrees is 0. So, I dot J is equal to 0. J dot K is equal to 0. And K dot I is equal to 0. How can we find the dot product of a vector expressed in terms of its components along coordinate axis? If two vectors A and B are expressed in terms of their components along coordinate axis AX, AY, AZ, BX, BY, and BZ respectively, then A dot B is equal to AXI plus AYJ plus AZK dot BXI plus BYJ plus BZK, which is equal to AXI dot BXI plus BYJ plus BZK plus AYJ dot BXI plus BYJ plus BZK plus AZK dot BXI plus BYJ plus BZK equal to AXI dot BXI plus AXI dot BYJ plus AXI dot BZK plus AYJ dot BXI plus AYJ dot BYJ plus AYJ dot BZK plus AZK dot BXI plus AZK dot BYJ plus AZK dot BZK, which is equal to AXBX into I dot I plus AXBY into I dot J plus AXBZ into I dot K plus AYBX into J dot I plus AYBY into J dot J plus AYBZ into J dot K plus AZBX into K dot I plus AZBY into K dot J plus AZBZ into K dot K. Substituting the values of I dot I, J dot J and K dot K as 1 and the values of I dot J, I dot K, J dot I, J dot K, K dot I and K dot J as 0 and simplifying, we get A dot B is equal to AX BX plus AY BY plus AZ BZ. It is also equal to BX AX plus BY AY plus BZ AZ, which is equal to B dot A. As the dot product is commutative, A dot B equals B dot A. Now, using the dot product, we can measure the work done as the dot product of the force and displacement, which is equal to FD cos theta. However, the work done can be positive, negative, or zero depending on the values of the angle between the force and the displacement theta. The work done by a force is positive when the angle between force and displacement is acute. That is, the angle is less than 90 degrees. An example of this is when an apple falls freely towards the earth. The work done by the gravitational force on the apple is positive. In this case, the angle between the displacement of the apple and the gravitational force is 0. Similarly, when a spring is compressed, the work done by the compressing force is positive. In this case too, the angle between the direction of the applied force and displacement, which is the compression of the spring, is 0. The work done by a force is negative when the angle between force and displacement is obtuse. That is, greater than 90 degrees and less than or equal to 180 degrees. In the case of a rising balloon as shown, the work done by the force of gravity acting on the balloon is negative, since it is opposite to the displacement of the balloon. In the example of a boy lifting a stone, the work done by the gravitational force on the stone is negative, as the displacement is against the gravitational pull. The work done by a force is 0 when the force is perpendicular to the displacement. Consider a block moved over a horizontal surface. In this case, the displacement is along the horizontal, whereas the gravitational force, which is the weight of the block, acts vertically downwards. Here, work done by the gravitational force is 0, since it acts perpendicular to the displacement of the body. As another example, consider a stone tied to a string, whirled in a circular path. Here, a centripetal force acts on the stone to maintain its circular path. Centripetal force is always directed towards the center of the circular path, whereas the displacement of the stone for an infinitesimal time interval is along the tangent to the circle at the point under consideration. As the direction of the force is perpendicular to the displacement, the work done by a centripetal force is 0. The SI unit of work is joule, which is denoted by the letter J, named after the famous British scientist James Prescott Joule. Thus, 1 joule is defined as the work done on a body when a force of 1 Newton displaces the body in the direction of the force by 1 meter. Now you will learn about the relationship between work done on a body by a net force and the change in its kinetic energy by using the work-energy theorem. According to the work-energy theorem, the work done by a net force on an object is equal to the change in its kinetic energy. We know that the kinetic energy of a body of mass m moving with a velocity v is equal to half mv square. Consider a body of mass m moving with initial velocity u and let the constant net force F act on it. At the end of displacement d, its velocity becomes v. We know from the equations of motion that v square minus u square is equal to 2ad. Multiply both sides with half m and simplifying, we get the expression as shown. We get half mv square minus half mu square is equal to mad. On the left side of the equation, half mv square is the final kinetic energy of the body, and half mu square is the initial kinetic energy. On the right side of the equation, we have the product of m, a, and d. According to Newton's second law of motion, ma is the force on the body. We have on the right side product Fd, which is equal to the work done on the body. This proves that the work done by a constant net force is equal to the change in its kinetic energy. We know that the work done by a force F on a body is W is equal to Fd cos theta, where d is the displacement of the body and theta is the angle between the force and displacement. But in practical situations, a body may be acted upon by a force which may not be constant and is a variable force. A variable force is a force whose magnitude or direction or both vary during the displacement of a body on which it acts. Let's look at an example of a variable force. As the spring oscillates between the extreme positions O and A, the restoring force on it keeps changing with the displacement from the mean position. This is a variable force on the spring. How do we calculate the work done by such variable forces? Let us suppose that a body moves along the direction of a variable force acting on it. We then plot a graph of force F versus displacement x, which helps calculate the varying force with the displacement. The work done by the variable force can be found by calculating the area under the graph. To find the work done by this variable force, we divide the total displacements into n number of small elements or segments: delta x1, delta x2, delta x3, and so on till delta xn. The work done with respect to the first segment, delta x1, is the area of this first segment, that is, F1 into delta x1. Work done with respect to the second segment, delta x2, is the area of the second segment, that is, F2 into delta x2. For the third segment, delta x3, work done is the area of the third segment, that is, F3 into delta x3, and so on. Here, we assume that the force remains constant for each small segment. Thus, the area of any segment will be denoted by the expression delta A is equal to Fx delta x. Let this be equation 1. The total work done is equal to the sum of the areas of all the small elements, which is equal to the summation of F delta x taken within the limits from x1 to xn, as in expression 1. If the size of each segment is very small, each segment tends to 0, and we have a large number of such segments. And the total work done is calculated as W is equal to sigma of F delta x between the limits x1 to xn, as the limit of x tends to 0. Let this be equation 2. Hence, the work done for a varying force can be expressed in integral form, as W is equal to integral f dx in the limits x1 to xn. Let this be equation 3. We know that according to the work energy theorem, the work done, W, by a net force on a body is equal to a change in its kinetic energy, Ke, as in expression 4. W is equal to delta Ke. Let us now try to prove the work energy theorem for a variable force. We know that the work done by a variable force can be found by the expression W is equal to integral f dx in the limits x1 to xn. Let's call this equation 5. If the velocity of the object at an instant is v, then its kinetic energy at the instant is expressed as half mv square. Let this be equation 6. On differentiating equation 6 with respect to time t, we get the rate of change of kinetic energy as dk by dt is equal to d by dt of half mv square. Thus, on simplification, we get dk by dt is equal to half m d by dt of v square. On further simplifying, we get dk by dt is equal to half m into 2v dv by dt. Thus, dk by dt is equal to mv dv by dt. This can also be written as dk by dt is equal to mdv by dt into v. On the right side of the equation, we know that dv by dt is the rate of change of velocity, which is the acceleration of the body. Thus, we get dk by dt is equal to mav. However, according to Newton's second law, F is equal to ma. Therefore, we get dk by dt is equal to fv. Also, the velocity term v in the expression can be represented as the rate of displacement v is equal to dx by dt. Hence, we get expression 7 as shown, which is dk is equal to f dx. Integrating expression 7 in the limits from x1 to xn for the displacement and for k1 to kn for the corresponding kinetic energy, we get integral dk within the limits k1 to kn equal to integral f dx within the limits x1 to xn. The left side of the equation indicates the change in kinetic energy, and the right side of the equation indicates the work done on the body by the variable force. Thus, we see that the work done by a variable force on a body is equal to the change in kinetic energy of the body. This proves that the work energy theorem holds true for a variable force. Now let us learn about potential energy. The energy stored in a body by virtue of its position or configuration is called potential energy. Consider a body of mass m placed on the surface of the earth. The weight of the body placed on the surface of the earth is denoted by mg. Let this be equation 9. To raise the body through height h above the surface, the minimum force required is its weight, which is equal to mg. Consider the upward direction to be positive. The work W done to raise the body through height h against the gravitational force of attraction by an external force is mgh. Let this be equation 10. This work is stored in the body as its potential energy. The gravitational potential energy of the body as a function of height h is denoted by V of h, and it is the negative of work done by the gravitational force while raising the body through the height. Thus, we have V of h is equal to mgh. If h is the variable, it can be easily shown that the gravitational force F is equal to the negative of the derivative of V of h with respect to h. Thus, F is equal to minus d by dh of Vh equal to minus d by dh of mgh, which is equal to minus mg. Let this be equation 11. The negative sign indicates that the gravitational force is directed downwards. Hence, when released, the body comes down with increasing speed, converting its potential energy into kinetic energy. The body strikes the ground with the velocity v denoted by the expression v square is equal to 2gh. On multiplying both sides of the above equation with half m, we get half mv square is equal to half m into 2gh, which is equal to mgh. The left side of the equation is the kinetic energy of the body on reaching the ground, and the expression on the right is the potential energy stored. Thus, this proves that the potential energy of the body is transformed into its kinetic energy when the ball is released. Hence, physically the concept of potential energy is applicable to the type of forces where work done against the force is stored in it. Mathematically, the potential energy V of x is defined for any force F of x, which can be written as F of x is equal to minus dV by dx, shown by expression 12. Integrating on both sides of the expression within the limits of initial position xi and final position xf. And on simplifying, we get minus of Vf minus Vi. On further simplification, we can arrive at the conclusion as shown in equation 13. Integral of fx dx within the limits xi and xf is equal to Vi minus Vf. From equation 13, we can see that the work done on a body by the force depends on the initial and final positions only, and not on the path followed by the body. Such a force is called a conservative force. By definition, If the work done by a force is independent of the path followed, then it is a conservative force. Such a force is characterized by equation 13. Gravitational force and elastic force, in the case of a stretched spring, etc., are examples of conservative forces. Let's try to understand these forces. We see that when a box is dropped from a certain height, the work done by gravity on the box is mgh. When the same box slides down the smooth inclined plane at an inclination of theta with the horizontal, the force acting down along the incline is mg sine theta. The distance travelled by the box is L. And hence, the work done by gravity on it is denoted by the expression W is equal to mg sine theta into L. On simplifying, we get work done as mgh as shown in expression 15. So far, we have studied conservative forces. Let us now learn about non-conservative forces. If the work done by a force depends on the path followed, it is a non-conservative force. For example, friction is a non-conservative force. Consider a box placed on a rough surface and moved through different positions A and B in different paths. In the first case, the box is moved along a straight path from A to B as shown. In the second case, the box is moved along a zigzag path from A to B as shown. The distance travelled is different in both cases. Hence, the work done to overcome the friction in both cases is different and is dependent on the path followed. Thus, friction is a non-conservative force. Consider a body of mass m.